I'd like to go over how you do an equilibrium problem. So in this video, I'm going to assume that you've worked some equilibrium problems, so you got the basic idea. What you just need is practice with all of those fiddling little steps, because really this is one of those things that happens so often in math and science where the idea itself is not that hard. There's just so many little steps to keep track of. So I am going to have us walk through an equilibrium problem. Let me share my screen with you folks so that you can see what I'm writing. Here we go. And I'm going to have us work the problem where something called nitrosyl chloride, which is NOCl, can go back and forth between nitric oxide, which is NO, and chlorine gas. And these are all gases, actually. There we go. So there's the balanced equation. Now, of course, if for some reason they didn't give you the balanced equation, then your first job is to take the verbal description. Nitrosyl chloride becomes nitric oxide gas and chlorine gas, and to balance it properly. But we'll assume that you've got that done and you're ready to work the equilibrium problem. So one thing you need is what's called the K value. The K value for this one is 1.6 times 10 to the minus 5. Now, a small k means that the reaction doesn't happen very much. Things stay pretty much on the NOCl side, whereas a big K would mean that things shift to the right and a lot of nitric acid and chlorine gas is formed. So your first task is to take that K value and set it equal to use what's called the law of mass action to write the expression concentration of nitric oxide squared, remember those little brackets mean concentration of, times concentration of chlorine gas rather, over concentration of NOCl, and that's squared. And there's one of those wretched little details that you've got to keep track of. Because of those 2's in the balanced equation, this 2 here translates to that 2 there. This 2 here becomes the power of 2 down in the denominator. Nope, said it backwards, sorry. This 2 here is this 2 here, and this 2 here is this 2 here. Let me just color code those so you can see it a little easier. That 2 becomes that 2, and this 2 becomes that 2. Okay, so if we only knew, well, basically, we want to figure out what are the equilibrium concentrations of everything. And this is where, well, first of all, we have to know what we're starting with. So let's say we're starting with that's not going to work. Let's say we're starting with 0.25 molarity of nitrosyl chloride. And let's say we start with nothing else. So I think with nothing else there, you can probably believe me that the reaction will go towards the products. But not much because of this very small value of K. Still, a little bit of product will get formed and we can figure out how much. This is where we make what a lot of people like to call an ICE table. And just because I can, I'm going to change color. So ICE stands for initial amount, change, and equilibrium amount. And across the top, we write the balanced equation: 2 nitrosyl chlorides, go back and forth from 2 nitric oxides plus chlorine gas. I forgot to put the 2 in there. By the way, somebody once asked me, don't I have to put a 2 here because of this little 2? And no, the fact that there's 2 chlorines in one molecule means that this is just to the power of 1. But the fact that there are 2 separate nitrosyl chloride molecules, that's what makes you put the power of 2 in that law of mass action. Okay, so now we're going to fill in the initial amount of NaCl is 0.25, and the others are 0. Now, a certain amount, an unknown amount of nitrosyl chloride will go bye-bye, and matching amounts of nitric oxide and chlorine will get made. But here's where we still have to take account of those 2's, because if there are 2 nitrosyl chlorides, then 2x is the amount that's going to go away. So we have to subtract 2x, which means the equilibrium amount will be 0.25 minus 2x. On the other hand, the nitric oxides, there's 2 of them. So 2x will get made, and 2x is the final amount. Chlorine, however, there's only 1 of them. Even though it's Cl2, there's only 1 molecule. So X is the amount that gets made, and X is the equilibrium amount. So watch out for keeping track of all those pesky 2's. Once again, I'll color code these here. Okay, now we got things that say what the equilibrium amount is, 0.25 minus 2x and 2x and x. But at least we can now plug those things in to our law of mass action equation. And we get the following: 1.6 times 10 to the minus 5 equals, the NO is 2x, and that's got to be squared. The Cl2 is x, and that stays to the first. And in the denominator, we have 0.25 minus 2x. There's an equation. Now, you may have a computer or a calculator that can solve this equation. If so, I have no problem if you use it. Plug it in, solve it. However, if you have something like a TI 83 or 84, or one of those where it doesn't have a built-in solver, I mean, you could still graph this equation and graph this line. You'd have to zoom to really see it, and you can find out where they cross, and that would be the solution. But because K is so small, you also have the option of saying, I'm going to simplify this a bit, because a small K means a very small value of X. That means that down in the denominator here, we are subtracting a very tiny amount, which means we can ignore it. Multiplying by a tiny amount has a big change. If I take 100 and I multiply it by the tiny amount 1/100th, that turns it into a 1. That's like huge change. But if I take an amount like 100 and I add a tiny amount like 0.1, 100.1, that's almost 100. That has almost no change. So we simply write our equation like this. In the numerator, we can take that 2x and square it to get 4x squared, and then combine with the other one to get 4x cubed. And in the denominator, we simply ignore the 2x. Don't care about it. And the result is we have an equation which is easier to solve, because this one, I mean, we still probably want a calculator to do the wretched math, but we can therefore say, I'm scrolling and I know that Zoom takes a little while to scroll. Okay, there we go, it's all good. Multiply both sides by 0.25 over 4, 0.25 over 4. And we have 0.25 times 1.6 times 10 to the minus 5 all over 4 is what x cubed equals. And we can plug all that into a calculator and cube root, or rather raise both sides to the 1/3 power, which is the same thing. And if you do that, you get the answer. X equals 0.0063. Well, we knew that was going to be a tiny amount, and so it is, so that's all good news. And now we can get the equilibrium amounts of both things. So for the NOCl, the equilibrium amount is 0.25 minus 2 times that pathetically small amount, which is again so small that we basically ignore it and say that the equilibrium concentration of the NOCl is about still 0.25 molarity. But the nitric oxide is 2 times that. And that is worth noting because there wasn't any before. So if we do 2 times 0.0063, we have 0.0126. I know there's rules of rounding and sig figs. I'm more or less ignoring that for the moment. And the chlorine gas, which is just X, then that would be 0.006. Let's try that again, 0.0063 molarity. And voila, there is an equilibrium problem which had just about everything you could have to deal with for an equilibrium problem in a high school chemistry class. Okay, I hope this video helps you solve equilibrium problems. Good luck to you. Take care.